Hello. Today we're going to talk about part one of the radical simplification. We're going to go over some of the sheet that I gave you and I gave you the answers to a couple of days ago. We'll be doing this for two parts. So today's part is part one, and this mainly deals with simplifying radicals and dividing by a single radical. So let's take a look. I'm going to share a screen here. This is the sheet that you had with the answers on it. And so when we think about a square root is nothing more than what you have to square to get the number underneath. So when you think of 36, it's 6 squared, so the square root of 36 is 6. Okay. Sometimes it doesn't, though, come out real well. In other words, sometimes we have, the square root of 75. The square root of 75 isn't a perfect square like 36, where we have 6 squared. So what we do is we look for the largest perfect square and another number that multiply out to be 75. So in this case, that would be 25 times 3, because 25 is 5 squared, and the square root of 5 squared is 5. Then the square root of 3, we can't do anything with. Now, no, this is the rule from the handout that I gave you, the other handout I gave you with examples and definitions. And basically, if you have a product of two or more things underneath the square root, you can take the square root of each part separately. And in fact, that goes for any type of radical, whether it be a square root or a cube root or a fourth root or a fifth root or whatever. So we look at 162 here. 162, the biggest perfect square in 162 is 81. 81 times 2 gives us 162. 81 is 9 squared. So the square root of 9 squared is 9. Because that's what we had to square to get 81 times the square root of 2 that we can't do anything with. Now, this little number here, that's the index. Let me get my cursor here. There it is. This little number right here, that's the index. So in this case, it's a 3. That represents a cube root. So that would be saying, what do you have to cube to get 108? Well, there's no number that you can third power and get 108. But just like with square roots, we can rewrite the 108 as the largest perfect cube times some other number. So in this case, it's 27, because 3 cubed is 27, and 27 times 4 is 108. Now, no, the 4 is not a perfect cube, unlike the 4 squared, or the 2 squared being 4 is a perfect square. So we do the cube root of 4. We can't do anything with it because it's not a perfect cube. However, the cube root of 27 is 3, because 3 to the third again is 27. So in number 5, we have a fifth root, or a fourth root rather. So the fourth root is 64. We're going to do the same idea. We're going to look for perfect fourth powers. So a perfect fourth power would be 16 for 16, which is 2 to the fourth power. And then the fourth power the fourth root of 4 is just 4, fourth root of 4. So the fourth root of 16 times the fourth root of 4 will be 2 from the fourth root of 16. And then again, I can't do anything with the fourth root of 4 because 4 is not a perfect fourth power. Now note, anytime you have a negative number underneath an even index, so a square root, fourth root, sixth root, you can't do it as a real number. Okay? The number underneath an even root has to be positive or 0. Okay, it can't be less than 0. If it is, then we just put the no solution symbol, which is the 0 with or the circle with the line through it, like we have in number 6. That just means there's no solution. Now here that we mean no real number solution. Okay. Also note that the number underneath the square root or a cube root or fourth root or any kind of radical is called the radicand, and the number beside it outside, right there, like the 3 or the 4, that's called the index. That's going to become important as we go further on and start simplifying things a little bit more. So let's simplify some radicals that actually have some variables in them. So the first radical we have is the square root of 27x to the 9th. Now we break this up into several parts. The first part we deal with the 27. The square root of 27 as before, would be the square root of 9 times 3. I'll take the square root of 9, which is 3 squared, and that gives us 3 times the square root of 3. That's where that part came in. Just the 3, not the x to the 4th. Now, where does the x to the 4th come from? If a variable has an exponent that's larger than the index, and it's an even index, like a square or a 4th power, then break that variable up into 1 minus the exponent times x to the 1st, or the variable to the 1st. So in this case, it's an x to the 9th. So I break it up as x to the 8th, 1 minus the exponent times x to the 1st. Why do we do that? Well, because then once we do that, we take this, whatever this power is, and divide it by 2. That gives us x to the 4th. That's the same thing as saying x squared, or x to the 4th squared gives us x to the 4th. Okay, so you take that number and divide it by the index. That goes outside of the radical. That goes outside the square root, or the 4th root, or the 6th root, or whatever even root you have. And then the x stays inside the square root. So now we put it all together. This 3 right there, that was in the square root, so it goes back in the square root with the x. This 3 was outside the square root, and the x to the 4th was outside the square root, so you get 3x to the 4th. So let's try that again. So for number 2, we have 98x to the 3rd, y to the 2nd. So let's take a look. The 98 is 49 times 2. 7 squared is 49. So it's a perfect square. Times 2, that gives us 98. So when I simplify that part, I get 7 square root of 2. Now doing what we did before, we'll take a look at this. So let's see, I have an x to the 3rd. So I write this part as x to the exponent minus 1 power. So that's going to be x squared times x. Okay? I divide the 2 by the index, which is 2. That gives me this x to the 1st. Now what about the y squared? Well, the y squared definitely is not, the square is the same value as the index. It's a square root, so the index is 2, even though it's not written. So we divide that out. 2 divided by 2 gives us 1. So that gives us a y to the 1st outside the square root. So we put this together. We have a 7, an x, and a y outside. And we have a square root of x and a square root of 2, of 2. And so we put those two together as a square root of 2x. Now, no, this is going to be confusing to some people, but we have to remember this, okay? Because of this part 6 here, you can't have a negative number underneath the radical. If we pull x out or y out or any variable to the 1st power out or any variable to an odd power out, we put absolute values around it to make sure everybody knows it's a positive value. Okay? Let's take a look at 3. So in number 3, we have an 81, the square root of 81, x, y to the 5th. So going through the same process, I do the 81 first. The square root of 81, well, 81 is a perfect square. It's 9 squared. So the square root of 81 is 9. The x, it's x to the 1st. Our index is 2. So it's less than the index. Therefore, it just stays in as square root of x. And then the y to the 5th, we're going to rewrite that as y to the 4th because that's 1 less than the 5th power times y. So when I divide out the 4 with the 2, I get y squared. That goes outside the square root. The y to the 1st stays inside. So that gives us a total of 9y squared outside. I don't need the absolute value there because the square is always positive. Okay? And then times the square root of xy. We do basically the same thing with cube roots, except we remember it's a cube root, not a square root. Okay? We have to pay attention to the index. So in this case, we have a cube root. So 162, the cube root of 162. I can write that as 27 times 6. Why 27? Because that's a perfect cube. That comes from 3 cubed. Oops, sorry about that. And then I do the cube root of 27, I get 3. I do the cube root of 6, that stays as a cube root of 6. So that's where that part comes from. Whoops, that part right there. Okay. Now let's take a look at the x. I have an x to the 9th. Okay. Times an x squared. Now where did I get that from? Well, when it's an odd root, an odd index, we take the biggest number that that index can divide with this. So in this case, it's 11. So the biggest number that in 11 that 3 will divide with is 9. What do I have to get 11? Well, 9 plus 2. So I write this as x to the 9th times x squared. So that means I divide the index just like we did up here. We divide the index with this 9th power. That gives us x cubed outside of the square root, the cube root. So that's where that part comes from. And then the x squared, that's less than the index, that stays in the cube root. Here we have a y to the 7th, so we do the same thing. Our index is 3. Okay, the largest number in 7 divisible by 3 is 6, because 6 divided by 3 is 2. So I write the y to the 7th as y to the 6th times y. Then I divide the y, or the 6 with the 3, giving me y squared. That's where this piece comes from, this y squared here. And then the cube root of y just stays behind. I can't do anything with the y. The index is bigger than the exponent for y. So we put it all together. The 6, the x squared, and the y go in the cube root. The 3 that we pulled out from 27, the x cubed we pulled out from x to the 9th, and the y squared we pulled out from the y to the 6th go outside. Okay, they go outside the cube root. I do not need absolute values for a cube root because a cube root can have a negative or a positive underneath it. It's only when it's an even power or an even root that I have to worry about that. Sometimes we see square roots and cube roots and all kinds of radicals dividing things. So let's take a look at a couple of examples here. Okay. In the handout I gave you that deals with rules and concepts of radicals, it talked about how we can take the radical of the top and radical of the bottom if we're dividing out, or we can take it all as one big divide. Okay. And so in this case, we have a square root of 27x to the 9th over 3 over the square root of 3x. These are separate square roots. So what I can do is I can either keep it this way if it helps me simplify, or I could put it all underneath one big square root with the fraction inside. And that's what I'm going to try if I can't see anything else to do. So I'm going to rewrite this as one big square root with the fraction inside as 27x to the 9th over 3x. And then I'm going to divide that out. I'm going to simplify that. So 27 divided by 3 gives us the 9, and x to the 9th divided by x gives us x to the 8th. And so when I take the square root of 9, 9 is a perfect square. It's from 3 squared. The square root of 9 is 3. I do my process of taking 8 divided by the index. It gives me 4. So let's give me an x to the 4th outside of the square root. Here we start out with a fraction inside one big square root. When you start out with that and you can't see any other simplifying to do with the fraction, then write it as 2 separate square roots, like we did here. So it'll be a 3x to the 7th over a square root of y to the 8th. Okay, I can't do much with the square root of 3x to the 7th. I suppose I could simplify that as x to the 7th. I could write it as x to the 6th times x. So we go a little further with that part. Pull out an x to the 3rd and write it as x to the 3rd times 3x, the square root of 3x. The y to the 8th, though, the square root of y to the 8th, that's going to be y to the 8 over 2. So that really should be y to the 4th. So I'm going to correct this one. So this one should equal x to the 3rd times the square root of 3x. And this should be a y to the 4th. Sometimes we have a scenario where, you know what, we have a fraction and there's a square root in the denominator I can't get rid of. Now, some people say that's perfectly okay. That doesn't bother me that much, but some people it really bothers. So what do we do when that's the case? Like we have in 7. We do what's called rationalizing. To rationalize a denominator means that you multiply both top and bottom by whatever the square root is in the denominator. So in other words, I have a square root of 2 here. So I multiply top and bottom by square root of 2. Why top and bottom? Because if I divide that out, that's 1. Whenever I multiply by 1, it doesn't change anything. What this does, though, in the denominator is it gives me the square root of 2 times the square root of 2, which is the square root of 4, which is 2. That gets rid of the denominator, the square root in the denominator. However, in the top, all I can do is multiply the 3 and the square root of 2 together and write it as 3 square root of 2 over 2. Now, sometimes people get very tempted about dividing this out. Okay, the square root of 2 over 2. Don't divide that out. Keep it the way it is. Okay, this 2 and this 2 don't relate with each other. This is in the square root universe. This is not. So they stay away from each other at this point. Okay? If I have a big fraction, or a big square root rather, with a fraction underneath, and I don't know what to do, what do? I take and I rewrite it as the square root of the top over the square root of the bottom. And then when I have the square root of 3 there, again, that bothers some people. So let's get rid of it. Let's make sure nobody's bothered about things. Okay? So we multiply both top and bottom by the square root of 3. Okay? So when I do that, I get the square root of 3 times the square root of 3 in the denominator, which is the square root of 9, which is 3. In the top, I have the square root of 5 times the square root of 3, which is the square root of 5 times 3, or 15. That's all the further I can go. Again, this 3 can't reduce with this 15 because they're in different universes. Square root universe, non-square root universe. Next time, we'll deal with addition, subtraction, multiplication, and finding the conjugate and some exponent problems. Okay, until then, take care.